chapter. The topics are basically probability in different theorems associated with the probability, such as addition theorem, multiplication theorem, Bayes theorem, understanding the different types of events. Then it also includes the random variable, continuous and discrete random variables, and random distributions. And from the statistics part, this topic consists of understanding the different measures of central tendency, such as mean, median, and mode, and different measures of dispersion, such as standard deviation, variance, and so. It also includes the correlation and regression. So this is the overall scope of this chapter, probability and statistics. We will start this session with the probability. So we'll first go through some standard definitions, and then we'll deep dive into understanding different types of events and different theorems in the probability, and we will look into some examples to understand the concept in more detail. Whenever we start, say, the probability, like we um, we associate it with it we associate it with the random experiment. If it is fixed experiment, if we know that this is going to happen, then it is for sure event. Then there is no need of finding the probability. Like say, rising of sun um, from the east. This is a sure shot event. We know like this is going to happen every day, and we don't have to find the probability for this event. If things are mean to happen, um, which are like for sure, then for those all events you can consider it as a sure events, and probability is not expected in that. Probability part comes into the picture whenever we have some random experiment whose outcome is not predictable. We cannot predict the final exact outcome. So example, if we toss a coin, if you roll dice, if you take any card from pack of playing cards, we don't know what outcome it will give. It may give any outcome. Let's say if you toss a coin, you'll get head or tail. Rolling a dice can give any number from 1 to 6, and picking a card from pack of 52 gives you any card and of any number. So all these examples where outcome is not fixed, or let's say unpredictable outcome, we call those events are random experiment, and probability concept makes sense in this. Sample space is the another definition. Collection of all the possible outcomes of an experiment is sample space. So as I have given the same example, we can take tossing a coin give you either head or tail. So how many possibilities are there? If you list it down, and that set will become your sample space. Same goes with rolling a dice. Rolling a dice is giving either 1, 2, 3, 4, 5, or 6. So this is the sample space for the for an experiment where you are rolling a dice. In same way, if you have, let's say, um, a cards, okay, pack of 52 cards. So there are 52 possible outcomes. So sample space in that case is 52. The next definition is event. Outcome of an experiment is called as event. So if I say, like, I have rolled a dice and I got an even number. Okay, so getting an even number is event. So either you can get 2, 4, or 6, or let's say if I take a card from a pack of 52 and I say I got a red card. So the outcome of that experiment is getting a red card. So whatever is outcome of the experiment, we call it as event, and the probability of that event is calculated by using formula number of favorable cases divided by total number of cases. So if I take an example of same pack of 52, I'm taking a card and the event is getting a a red card, it means out of 52 we know 26 cards are red. So 26 divided by 52 is your probability, or 1 by 2 is your probability, right? So because number of favorable outcomes is 26 and total number of cases is 52, you will end up with the 1 by 2 as answer. Yeah. Number of favorable outcomes, if you denote it by m, and total number of cases means your sample space, you denote it with n. M is always less than or equal to n. M can never be greater than n. So we can say that the probability is always greater than 0 and it is always less than or equal to 1. If probability is equal to 1, we know that is a sure event. And if probability is 0, that is an impossible event. So we are talking about the cases or the events which are possible. So that's why the range of probability is always greater than 0 and less than or equal to 1. So this is all about the basics. We will proceed towards next slide where we'll try to understand in more detail about the different types of events. In probability, events are generally categorized into these three cases, like, or these three events: dependent events, mutually exclusive events, and independent events. Generally, students feel some confusion into this, but I think these Venn diagrams on the left hand side will give you the clear picture about its definition and how they are different from each other. So whenever we are talking about two events can be dependent, they can be independent, they can be mutually exclusive. So let's try to understand it in more detail. If occurrence of one event changes the probability of another event, then those two events are called as dependent events. Okay, we have two events happening, and occurrence of one event is changing the probability of occurrence of another event. We call it as a dependent event. Let's take an example here. I have again a pack of 52 and I take a card out of it. Let's say the card is red. Probability of getting red card is 1 by 2, because 26 by 52, you got 1 by 2. Now, I'm not keeping that card back into the deck. I'm taking another card out. And what will be the probability of getting a red card again? It will be now 25 divided by 51. So you can clearly see here, previously there were 26 cards and total cards were 52. You have taken one out. So the probability of next event now is depending on what is occurred on the previous event. If let's say in previous event you got the black card, then you have 26 red cards. So in that case, probability would be 26 by 51. But now if you got
Sir, I request you to write while explaining.
yeah, okay.
Thank you.
Just let me add one slide here to explain it in more detail. So we have pack of 52, and as I said, first card is taken out, and let's say it can be red or black. And now we are not replacing it. Now total number of cards are 51. And let's say the occurrence of the second event, let's say if you get the red card, then it will be considering previously you got the red card, you have the probability of 25 divided by 51. And imagine you got black card in the first step, then getting a red card probability will be 26 by 51. Okay, so this is probability of getting a red card in second attempt. Okay, so we can clearly see here whatever has happened in first attempt. This is your first attempt. Okay, this is the first attempt, and this is the second attempt. So whatever happened in the first attempt is affecting the probability of um, whatever is happening in the second attempt, right? So in this case, I'll call these events are dependent because occurrence of an event changes the probability of occurrence of another event. Imagine now if I don't keep that card aside, I'll just keep that card back into the deck. So in this case, this 51 will change to 52, right? So this 51 will change to 52. So it is same as taking a new card from a new deck. I'll repeat what I'm doing now. I'm taking a first card out and putting back into the same deck. And then if I do my second attempt, it is same as taking a card from a new fresh deck, right? So your sample space is now again new. So I will call that as an independent event. So I hope you understood the difference here. Dependent events, occurrence of an event changes the probability of another event. Then we can say that these two events A and B are dependent. But if occurrence of an event does not affect the probability of another, we call it as independent. The example which I have given, you have, let's say, two pack of 52s, and let's say I'll write it here. You have one deck here with a 52 card, another deck here with a 52 cards. Whatever is the probability of getting a black card here, let's say, and probability of getting a black card from this deck is independent of each other. Okay, because we are talking about two separate decks. Whatever we get in the first from the first deck doesn't affect the probability of whatever we'll get from the second deck, right? Because of two sample space. So these are the situations where we can say that our sample spaces are like new or different. And the same situation I have explained here. If you take a card from a deck and one of the event is occurred, and now you're putting back that card into the deck. Again, if you perform a second experiment, then it is the sample space is like a new sample space, right? Because again, that deck is having 52 cards. So that's why it is like a separate or different sample space, and we can call it as a independent events. So independent and independent events, you can clearly see here we have different sample space S1 and S2, and here we have same sample space. In mutually exclusive events, what is how they are different compared to dependent and independent? The events that do not occur at the same time, we call it as a mutually exclusive event. In this case, we are talking about the same sample space. So again, I'll give an example of a deck with the 52 cards. Getting a black card, what is the probability of getting a black card? Probability of getting a black card from the pack of 52 is 1 by 2, and getting a red card probability is again 1 by 2. But we cannot have let's say, an event where we'll get both black and red card, right? Because you are taking only one card, there is no card which is both black and red. So probability of occurrence of both the events is 0. Okay, so we are talking about the same sample space here. We are talking about only one deck of card, and that is why these two events are mentioned in the same sample space. So you can easily now relate dependent and mutually exclusive. Dependent events have some intersection between them. A and B have some intersection because occurrence of one event changes the probability of another. In case of mutually exclusive event, these two events are separated. They cannot occur at the same time. Here, this is the possibility A and B can occur at the same time, and that is why they are dependent on each other. In this case, they cannot occur at the same time, so they are mutually exclusive. Events that do not occur at the same times in the same sample space, we call it as a mutually exclusive. And occurrences of an event does not affect the occurrence of another. Okay, then we call it as a independent. So again, another example would be, let's say, a coin. If you are tossing a coin, you will get either head or tail. You cannot have head and tail at a time, right? So getting a head and getting a tail in a coin are mutually exclusive event, right? If you have two coins, whatever outcome in the first coin and the second coin are independent of each other. Okay, because the sample space for the first coin, sample space for the second coin is different, and that is why that will be an example of a dependent event. Okay. Uh, if you want to understand it in more detail, I would also like to give you an example of a dice. When you roll a dice, 1, 2, 3, 4, 5, and 6. These are the outcomes. You let's say event A says getting a even number, and event B says getting an odd number. We can clearly see A and B are mutually exclusive. We cannot have a even number and odd number at a time. So A and B are here mutually exclusive. I hope you understood all three events in detail. If you have any questions, feel free to ask. Okay, coming towards the next slide. I think, yeah, this is one example which uh, where I will explain now, with and without replacement, how the same events are becoming dependent and independent. So I have a pack of 52, and let's say event A says getting a king. 4 by 52 is the probability of getting a king because there are 4 kings. And now I'm not putting that card back into the deck. So probability of getting the king again will be 3 by 51, because now total number of cards are 51 and only 3 kings are left because 1 king you already got. So that's why 3 by 51. However, if you do the replacement, means if you put that card back into the deck, the probability in first case is 4 by 52, and also in the second case 4 by 52. So A and B are independent events here, because in the second case it is same as you are taking card from the new deck, okay, or having a new sample space. So this is how we can, let's say, differentiate the examples, um, where the replacement or without replacement wording is used. You should clearly identify that if it is without replacement, that is about the dependent event. If with replacement is mentioned in the question, those questions belongs to the independent events. So that is about the different kinds of event. Now it's time to deep dive into the theorems in the probability. We will discuss about the complement theorem, addition theorem, multiplication theorem, and the Bayes theorem, and we will also look into some examples of it. So starting with the complement theorem. Complement theorem is like P of A indicates probability of occurrence of event A. Probability of A complement indicates probability of not occurrence of event A. So probability of not occurrence of event A is equal to 1 minus probability of occurrence of A, because sum of all the probabilities is 1. We know probability of occurrence of A plus probability of not occurrence of A is 1, and from that we can clearly write down these two formulas. Okay, so let's take an example. We have a dice. We are rolling a dice. The outcome can be 1, 2, 3, 4, 5, or 6. So probability of getting 1, 2 is equal to 3, is equal to 4, is equal to 5, is equal to 6, and is equal to 1 by 6. So 1 by 6 is the probability for getting any number when you roll a dice. So if I say, what is the probability of getting 1? 1 by 6. What is the probability of not getting 1? Is 1 minus 1 by 6, and that is 5 by 6. Why? Because there are 5 possibilities. If you don't want 1, you it means you want 2 or 3 or 4 or 5 or 6. So there are 5 possibilities out of 6, which will give you the probability of 1 complement, means probability of not occurrence of 1. Okay, very easy. Next one is addition theorem. If A and B are dependent, and if A and B are independent, this theorem will slightly change. Okay, let's see when, in which cases we should go for addition theorem. Whenever we use term or in our sentence or in the question, if you come across word called as or, like this, or in the case like you are okay with this or that, means you are open for more possibilities. Whenever this or is used, it means two probabilities will get added together and overall probability will increase. Let's take an example. I'm rolling a dice, and if I say I want 3 or 4, so get, if I say I want 3, probability is 1 by 6. If I say I want 4, probability is 1 by 6. But if I say 3 or 4, the probability is 2 by 6. So whenever we are using or, we are basically adding the probabilities together. So we are increasing our chances, right, of getting that outcome. So whenever we use or statement, it means we are increasing the possibilities or increasing the probability. Okay, or we are, let's say, reducing our constraint. As you keep on adding the constraints, I want this and that, your probability will reduce. Okay, but if you are more open, let's say I want this or that, chances are more and more, right? So it's the same. Yeah, so let's look into in more detail. Whenever word is or is can be written in terms of addition, or you can also say as union. Probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B in case of dependent events, whereas in case of independent events, probability of A union B is equal to probability of A plus probability of B. Sorry, in case of mutually exclusive events, probability of A union B is equal to probability of A plus B. Here you will not have A intersection B, and that's why this term is not included. Why we are subtracting here? You can clearly see this part you are considering two times when you say probability of A plus probability of B. Probability of A is this, right? And probability of B is this. Means this intersection part you are considering two times, but ideally it should have been considered only one time because you are talking about this curve. You are not, let's say, you should remove this consideration of this shaded area, blue shaded area two times. So that's why one time we are subtracting it, and so that we'll get the red color shaded area. Okay. However, in this case, A and B don't have an intersection since they are mutually exclusive events. We don't have this term. Probability of A plus probability of B is your probability of A union B. Okay. So now I'll give one simple example for this. What is the probability of die showing number 3 or number 5? So probability of getting 3 or 5 means probability of getting 3 plus probability of getting 5. 3 and 5 you cannot get at the same time. So that's why getting a 3 or getting a 5, these two are the mutually exclusive one, and that's why this formula you have to use probability of A plus B. You will not have term probability of A intersection B. Probability of A is 1 by 6, probability of B is also 1 by 6. 2 by 6 means 1 by 3 is the final answer in this case. I hope you are following. Okay, feel free to ask you in case of any doubts. Coming towards, so whenever you get any question, look into the words, what kind of words they are using, whether they are using or, whether they are using and word. So these words makes difference. If I say probability of showing getting a number, let's say 3, or let's say mm, if I phrase it differently, I'm rolling a dice. What is the probability of getting a odd number and a prime number? So I'm putting more constraint. That number should be odd and also should be prime, right? I'm putting more and more constraint. Now, if I say what is the probability of getting when you are rolling a die? What is the probability of getting a either prime number or odd number? So in these two situations, you will get different value of the probability, because in when you are using word and means your requirements are more, your constraints are more, so your probability will be less. Okay. When you are using word or, it means you have less constraints. You're little bit opening your constraints, and because of that, your probability will increase, and that is reflected in by the addition theorem. Okay. So as I have given you a hint now, in addition theorem, we are using addition. Okay, the probability value will increase. However, in multiplication theorem now, we'll see your probability value will reduce. Okay, so this is a summary here. When you use or, it means we are reducing the constraints and increasing your probability. You can relate or word with a union symbol or addition symbol. Whenever you are using and word in any sentence, it means you are increasing constraint. So what is the probability of getting odd number and a prime number when you roll a dice? It means you want a number which is odd as well as prime, correct? So that is increasing the constants. So it lowers the probability. So in that case, you have to multiply those probabilities. So you'll use the multiplication theorem, or that can be written as a and that can be written as a symbol intersection. Okay, union is for or, intersection is for and. Let's understand the multiplication theorem in more detail. In case of dependent events, probability of A intersection B is equal to probability of A into probability of B when A is already occurred, or probability of B into probability of A when B is already occurred. If the events are independent, probability of A intersection B is directly probability of A into probability of B, because occurrence of one event does not affect the occurrence of the another event in case of independent events, and that's why here this probability of B when A is already occurred is equal to probability of B in case of the independent events, right? And that's why if I let's say show here, probability of A intersection B is equal to probability of A into B in case of independent events. I'll explain with the examples later. At this point, you should understand here how the formulation is different in case of dependent and independent. Independent, probability of A intersection B is equal to probability of A into probability of B when A is already occurred. Whenever we write probability of B slash A, it means probability of B when A is already occurred. You have to phrase it like this. You can also phrase it like probability of B given A, probability of B given A. Okay, and this is called as a conditional probability. What is the condition here? A is already occurred, and now you are trying to find the probability of B, right? In this case, B is already occurred, and you are trying to find the probability of A. So these are the symbol is for the conditional probability, and that comes into the picture in case of dependent events. Let's take an example, and we'll try to understand how we will deal with the multiplication theorem. Let's say you have a bag with the 10 marbles. Out of these 10 marbles, 2 are black, 4 are red, and 4 are green color marbles. What is the probability of getting 2 black marbles one after the another? Okay. What is the probability of getting 2 black marbles one after the another? You can also phrase this question as what is the probability of getting, let's say, you are getting a first black marble and a second black marble, right? I can phrase this as A is probability of getting a first black marble, and B indicates probability of getting second black marble. So I can phrase it right. Probability of getting first black marble and a second black marble, right, is our question. So I'm using word and in this case. It means it is a multiplication theorem. Getting a black marble probability is in first case is 1 by 10. Sorry, 2 by 10 because there are 2 black marbles. So 2 by 2 is the number of possible outcomes. 10 is the number of total number of, sorry, 2 is a number of favorable outcomes and 10 is the total number of possible outcomes. So 2 by 10 is our probability. Now we are not putting that black marble back into the basket. So total number of marbles are now 9, and out of which only one is black, and that's why the next probability is 1 by 9. Okay, and hence it is a conditional probability because we are considering probability of B means probability of getting a second black marble provided that we got first marble as a black, right? And that is why we are writing it like this: probability of B given A. So 2 by 10 into 1 by 9 gives you 1 by 45. So I'll repeat. Whenever you use the AND word, it means multiplication. In this question, they are asking us to find the probability of getting first black marble and the second black marble. Probability of probability of first black marble is 2 by 10 and is multiplication. Probability of getting second black marble is 1 by 9. Why? Because it is probability of getting second black marble provided that the first marble is black. Okay, so that is why it is 1 by 9. We'll get 1 by 45 as answer. Now let's look into a similar question or the same question with the independent events. Okay, as I said, independent events are those where occurrence of one event does not depend on the occurrence of the another event. And the formula is now probability of A intersection B is equal to probability of A into B. Here we cannot write probability of B given A because probability of B given A is equal to probability of B, right? So this, in this case, in case of independent events, probability of B given A is equal to probability of B. Okay, and that's why this is the case. And why this is the case? Because occurrence of one event doesn't affect the occurrence of the another event. I have the same example here, but the phrasing of the question is a little bit different. We have again 10 black marbles, out of which what is the probability of getting 2 black marbles, one after the another. Till this point, question is same. Now the difference is given that you put first marble back into the box. Okay, so when you're putting the first marble back into the box, it will your sample space is again a new sample space or fresh sample space, correct? So in this case, probability of getting first black marble is probability of A, that is 2 by 10, and you're putting that marble back into the back into the box. So your again sample space will become 10, and again get probability of getting a black marble is 2 by 10. So this is the difference here. This is your probability of B here. And in previous slide, if I go here, this is the probability of B given A. Okay. This is how you should identify the difference in case of dependent and independent event, and how the formulation will affect into the multiplication theorem. Okay. So answer here is 4 by 100, 1 by 25 is the final answer. I hope you are following these points.
Any doubt, guys? Vishant, Tushant, Varun, Cynthia,
Yeah, feel free to
Manu.
ask in case of any questions. Okay.
No, okay. Please continue.
I'll proceed to the next slide. Here again, I have one different question, and let's understand the question in more detail. Formulation will slightly change in case of three events. I'll write it here. Let's say we have now talking about three events: probability of A, intersection B, intersection C. Let's say A, B, C are independent event, then the formulation will be probability of A into probability of B into probability of C. If the events, okay, if the events are dependent, then probability of A intersection B intersection C will be probability of A into probability of B when A is already occurred into probability of C when A and B is already occurred. Okay. This is how you can write the formula. Yes. Okay. So this is for the three events. And this was the formula in case of two events, A and B. So the question I have now is for the three events. Let's see how to deal with it. We have 5 black balls, 7 red balls, and 6 green balls are there. 3 balls are drawn at random, one after the another, without replacement. So it's a clear in the question without replacement. It means it is a case of independent events. Okay, it means we should use this formula in this. Okay, occurrence of one event depend on the occurrence of the another event. Find the probability of getting. First question, all black balls. So we have 5 black balls. Total number of blocks are 5 plus 7 plus 6, 18. Probability of getting first black ball is 5 by 18. Very clear. But when you took the first black ball out, now total number of blocks are 17, and out of which only 4 are black. So that's why the probability of getting second black ball when first is taken out, so that is probability of B2 when B1 is already occurred, is 4 by 17. Okay, multiply by probability of getting third black ball will be now 3 by 16, because after taking two balls out, the total number of balls are 16, and out of which only 3 are black because first two we have already taken out. So all black balls, you can also phrase it like probability of getting first black ball and second black ball and third black ball. So I'm using and word here, and that is why I'm using multiplication in this case. Okay. So I hope you're following why we are using multiplication theorem, because they are asking what about the probability of getting all black balls. It means probability of getting first black ball and probability of getting first black ball and second black ball and third black ball, right? Probability of getting first black ball is this. Probability of getting second black ball given first is already black is this, into probability of getting third black ball given first and second is black is this. Okay, so 5 by 18, 4 by 17 into 3 by 16 is your final answer. Imagine if they ask the same question with replacement. Okay, if this is with replacement, the answer would be 5 by 18 multiply by 5 by 18 multiply by 5 by 18, because in that case your sample space is remaining same again and again, because whatever you are getting you're putting back into the box. Okay, I hope now you're following dependent and independent even, and when to use the multiplication. uh, the second question here is balls of different colors. So let's say first is your black, so 5 by 18. You can take any sequence doesn't matter here. I'm taking, let's say first is a black, so 5 by 18. Second is a red, so total red are 7, but total balls are now 17. And the into probability of getting green, so um, green are 6, but now total is 16. Look at this number, like even if you interchange this 5, 7, 6 anywhere, your overall numerator and denominator remains same. Here order doesn't matter. Okay, so we have one question here. Let's see from Ne. In the second part, the answer should be multiplied by 6. Uh, yeah, balls of different color. So basically, mm, yes. So basically here, what we are doing, if I get a first black ball, then let's say second one is red and uh, third one is green. That sequence doesn't matter. Okay, we are not, let's say, doing arrangements here. Okay, we are just um, if you multiply by 6, you will end up with the arrangements. Okay, nay, we are not finding the arrangements here. We are just, let's say, finding the cases where you will end up with, let's say, one black, one red, and one green, and you will end up with 35 by 816 possibilities. Okay, it can happen like um if you end up with, if you are multiplying with 6, or if you go on, let's say, changing the sequence, what you will get is this different sequences, like because you have 5 black, 7 green, and sorry, 7 red and 6 greens. We don't care out of 5 black balls which one you are getting, out of 7 red which one you are getting, and out of 6 green which one you are getting, right? So we are not bothered about, we are just bothered about the colors. And also we are not bothered about the sequence, like whether your first black is ball, sorry, first one is a black ball, or second one is which, and third one is which. Okay, so that is why we should not let's say consider any multiplier in this case. I hope it is clear. The last question, two black and one green. So first ball is let's say black. Total number of balls, black balls are 5. So 5 by 18 is the probability. Now we want second is also the black ball, provided that the first one is black. So it will be 4 by 17, right? 4 by 17. And now we want third one is a green. So we have taken two balls out of 18. So only 16 balls are left. So that's why total number of outcomes are 16. Out of which we know 6 are for sure green, because the twos which we have taken out in first and second event are the black ones. So that's why 6 by 16 is the probability of third event. So what we are saying here, first ball is black, and the second ball is black, and third ball is green. Okay, so that's why and I am using, so I am multiplying all these three probabilities. So 5 by 18 is probability of getting first black ball, multiply by probability of getting second black ball, provided that first one is black, which is 4 by 17, and the probability of getting third black ball is 6 by 16. Okay, I hope it is clear. Question 3. In case of any doubts, let me know. Okay, we have another question here. First, is B, second one is G, and third one is R. B, G, R is also valid. Yes, so right. Yeah, so in this case, what they are asking is ultimately if you do that combination, first one is black, second one is a green, and third one is a red, the probability is same. Okay. Um, your numerator will always be like 5 into 7 into 6, or 7 into 5 into 6, or 6 into. So basically this is just an arrangement of your numerator. Your values will not change. Okay. And that is why let's say the value in this case is 35 by 816. Yeah, you should not consider here the cases like where you will have uh, what we can say, where you will have first one is black case, or first second one is black, and or third one is black. Okay, so that part you will do when you want to do the arrangements, not in terms of the probabilities. Okay, any other question? Okay, I'll go to the next slide. Yeah, let's look into this question. Yeah, this is again another theorem where we will talk about the combinations like complement theorem and let's say the addition theorem. Okay, let's look into this in more detail through Venn diagrams. We have two events A and B. Let's say your sample space is this. This is your event A and this is your event B. I want to find the probability of event A and not B. Means I want to find this red color, um, probability of this red color. Okay, so let's say you want to find the probability of A, but without possibilities of B. Okay, you don't want to consider intersection B part. So it is very clear from the Venn diagram, that is probability of A minus probability of A intersection B gives you probability of A intersection B complement. The meaning is probability of A and not B. How you should read it is like probability of A and not B. Okay, probability of A and means yeah, you are putting some constant, and not B is like your intersection part. Okay, so basically you don't want this intersection part, and which is A intersection B. That is what you are subtracting from here. Same goes with this. When you want to find this probability of B, then how will you read this? Probability of only B, it means probability of B and not A. You can also read it as like probability of not A and B, or probability of B and not A. It will be probability of B minus. So this whole circle minus this intersection gives you the probability of red color. So probability of A intersection, sorry, probability of A complement intersection B is equal to probability of B minus probability of A intersection B. I hope it is clear. I'll go to the next slide. Yes, here we are talking about the probability of the outside sample space. Means we don't want both A and B. So neither A nor B probability. So I'll say maybe you are rolling a dice and you don't probability of getting neither 2 nor 3, like that, right? Probability of getting or let's say what is the probability of getting neither a odd nor a prime number when you roll a dice, right? This is an example. You in this is the perfect case which is suitable for this figure. So probability of A complement and B complement means probability of neither A nor B is equal to probability of A intersection B, sorry, not A intersection B, A union B complement. Okay, let me union B, let me correct it. It's a probability of A union B because A union B is this unshaded color and its complement will be the red shaded color. So it is 1 minus probability of A union B. This is the case where you can clearly see probability of only A or probability of any of A and B at a time. Okay, not together. Probability of A or B, but not A and B at a time. Okay, this is how you can phrase it. So probability of A triangle B, this indicates like only one at a time, A or B, not together. Okay, so that's why we are not considering the intersection part. Either this is fine or that is fine, but not together. So that you can just add these two cases. This first case is this, second case is this. You just add them, you'll get this probability of A intersection B complement plus probability of A complement intersection. What we understand from this all cases is Venn diagram plays an important role when you want to derive any formulation. So whenever a complex problems like this comes, you can easily solve it by drawing a Venn diagram. Look at this. Just by looking into this Venn diagram, if I want to find this particular area or this particular probability, it is pretty clear that probability of A minus this shaded color. Here, same thing, probability of B minus intersection. The next slide, it is 1 minus probability of A union B. In this case, it is probability of A intersection B complement plus probability of A complement intersection B. Okay, so pretty clear. So like this, you can make use of Venn diagrams whenever you feel any difficulty in deriving the formulation. Okay, yeah. Um, so this is again we'll come to some more formulation part. Probability of A and B. Probability of A and B is equal to probability of A into probability of B. We know in case of independent events, and in case of dependent events, we know probability of A and B is equal to probability of A into probability of B when A is already occurred. Okay, we have already seen these two formulas in case of multiplication theorem. Okay, so either you can write it like this, probability of A first into probability of B when A is already occurred, or you can write it as probability of B into probability of A when B is already occurred, right? Uh, and you can also leverage this formulation in complement theorem also. Probability of A complement intersection B is equal to probability of A complement intersection B divided by probability of B. And yeah, you can just derive or further it. You already derived the formula for probability of A complement intersection B is this part, which is probability of B minus probability of A intersection B divided by probability of B. And if you just break it down here, these two terms will get cancelled. So it will be 1 minus probability of A intersection B divided by probability of B. Okay. And what is this? This is probability of A when B is already occurred. So you can conclude that probability of not occurrence of A when B is already occurred is equal to 1 minus probability of occurrence of A when B is already occurred. So this is how you can derive new formulation by making use of the Venn diagram formulas which we have just seen. Okay, so yeah, in the same way, we can also derive probability of A given B complement and probability of A complement given B complement. Okay, and yeah, these are the formulas for it. Okay, the base formula for this is I'm writing probability of A given B is equal to probability of A intersection B divided by probability of B. Okay, so with this we are writing this. You can clearly see A intersection B. So here A intersection B is not here. Here it is B complement. That is what we are writing. Here it is B complement. Again, we have derived the formulation for this. That is what we are writing here. Same goes with this as well. So this is about the combination, like when you use the multiplication, when you use the multiplication theorem and also the complement theorem together. Any questions so far?
Hello, sir.
Yes.
Yeah, so somebody asked doubt that is clarified, right? That's in
Yeah.
the
Yeah. That is.
second part. Okay,
Yes. Yes. That's clarified. Yes.
so I think we are done.
Yeah, sir. Yeah. I think we can. We are done.
Okay, so guys, how was the session? Any doubt?
Yeah. I think maybe let me just come back to this question. I'll. Yeah. I think I'll clarify it and then maybe we can answer once again. I think
Yeah,
this
sure.
is need to be clarified once. Um, just let me add one slide. Okay. So coming back to question, this is 5 black, 7 red, and 6 green. It's 5 black, 7 red, and 6 green. Okay, and the question is find the probability of getting balls of different color. So yeah, I'll maybe phrase it different way. So we will solve this problem by combination theorem. Sum of favorable outcomes divided by sum of possible outcomes. So indirectly, out of this 18 balls, we are taking 3 balls out. So 18C3 is how you can write. And yeah, so we will take one black ball, then we will take one um, red ball out. Sorry, 7C1, and we will take one 6C. Sorry, let's see 6C1. And sorry, it's a multiplication here. Okay, so let's like this, by using combination we can solve it. 5C1, 7C1, 6C1. So it will be 5C1 is 5, 7C1 is 7, and 6C1 is 6 divided by 18C3 is like 18 multiplied by, or 18 factorial divided by 3 factorial into 15 factorial. So let's say 18 into 17 into 16 into 15 factorial you can write, and you can cancel out these two terms. Yeah, so 3 factorial will go up. So 5 into 7 into 6 multiply by 3 factorial divided by 18 into 17 into 16. So yes, I think yes, in this case we need one correction. It's right to multiply with 6, and this is the final answer. Yeah, so I think this is the only correction uh, about the clarification um, from the second question.
Oh, thank you.
Yeah, thank you all for joining this session.
We'll wind up. Thank you.
Yeah.